Okay, so for our second talk of the day, we have Constanza Rojas-Molina from, I don't know how to pronounce it, well, Sergi, Paris, and she's going to talk about random Schrödinger operators, integrated densities of states, and localization.
Thank you, Daniel. Well, thank you. I thank the organizers for this invitation, for the opportunity to be here with you today, and also thank you to everyone that's here online. I mean, we have had a long year of a lot of Zoom, and I do appreciate that you're still online, and I thank you also for organizing this nice event. I apologize for not being here today. Yesterday, sorry, because here we're finishing the semester, so we're really, dealing with grades and finishing everything before the holidays start. So today I want to tell you a bit about random Schrödinger operators and give a brief introduction, and also show you a couple of examples where we see Schrödinger operators today. I mean, this is a bit of an old theory that started in the late 70s that has been very well developed in the literature, but there are still some very basic questions open, and I want to tell you a bit about this and the connections also to random walks, which is at the moment still being explored. So the motivation that we have to look at random operators is that we want to study how electrons propagate in materials. And we know that materials can be conductors or insulators. So we know that when we pass an electric current, so therefore we induce a current of a movement of electrons, we can see two possible behaviors. The electrons propagate, means the electric current goes through the material, in which case the material is a conductor, or the material does not propagate the current, the electrons stay localized, and then we talk about the insulator behavior of the material. Well, Philip Anderson, a physicist, discovered in the late 50s that if the material had impurities, maybe because of it was an alloy material and there were some defects, then this was enough to suppress the propagation of electrons, and then the material became an insulator. And it became an insulator because of the presence of disorder. And he got a Nobel Prize for this, and he proposed a model to study this. And this is what we call today the Anderson model. And this is the basis of the whole theory of random Schrödinger operators that gives a mathematical framework to study this behavior of when a material becomes an insulator by the effect of disorder. So what we do is that we consider all possible configurations of the material. So we assume that on every point of the lattice, we have an atom, and it can be of different types, since we don't know exactly if there are different species of atoms, or if we have a dislocation, we could also model it in this way, and with the positions of the lattice. And now in this picture, I just have the standard Anderson model, which is that on each point of the lattice, we put a random variable. And our operator is there for the minus Laplacian in the discrete setting, and plus a multiplication operator that is this random potential. So on each point of the lattice, what this does is to take this function that lives in our space L2 of ZD and multiply it by this random variable. Now, if you look, this can also be defined in the continuous setting in L2 of RD, in the whole RD space. And the potential would look something like this. So you see, it's a random landscape of hills and random hills and valleys. And we assume that it's quite regular for technical purposes. And in the discrete setting, we have a landscape of on each point of the lattice, we have a certain height. So this is the model. And now we want to study, how do electrons propagate in the material? And the energy of the electron is modeled by this operator, minus Laplacian plus the omega. And since we're in the setting of electrons, we're talking about quantum mechanics. So we're looking at Schrödinger equation. And if we want to study how the electron propagates, then we have to see how this solves. We have to look at the solution of Schrödinger equation. This is what governs the dynamics of the electron. And this is given by, well, an initial state, an initial condition. You can think of it as something very localized. If I've written this in L2 of RD and little L2 of ZD, but just to continue with what we were seeing in the previous talk, think of L2 of ZD. Our initial state can be delta, in delta concentrated at 0. And then we let this evolve under the action of a unitary group that is generated by this operator, H omega. Now, this operator is random. And what is the first manifestation of this disorder? And what is actually the description of what Anderson observed? And this is what we call dynamical localization. So we say that there is localization if we are in an interval, and usually near a spectral gap. This is usually, we can see this either if we assume that the disorder is very strong, so our hills are very large, are very high, or if we are at a very low energy in the spectrum. So near the wherever the spectrum starts, or it has a gap near there. And we look at this part of the spectrum, and the following happens. If we take any function in our Hilbert space with compact support, that is localized in space, and we let it evolve under the action of our random operator, so according to Schrödinger equation, and then we look at the position. So here we're taking, this is a multiplication by the space coordinate to a certain power. And what this quantity here is doing is to measure the concentration of our function evolved on time. And in order to have localization, what we're asking is that this function evolves on time, and it should be near the starting point. It should stay near the starting point for all times. Now, remember that this is a unitary group, so the mass of the function does not change. It's always a function of norm 1. Okay, so there is no dissipation here. The mass, the norm stays the same, but the question now is, where will the mass be concentrated? And if we start with something that is very concentrated, say near the origin, then this is telling us that as time evolves, for large times, if you want to think about that, the function will stay in a bounded region of space for all times. So this is what we call localization. And of course, this is a random operator, so we're dealing with several configurations. So we need to have these estimates in expectation. So we ask that for many of the configurations, actually all the statements fall almost surely. For almost every configuration, we see this behavior. So now this has
Constanza?
Well, yes?
Sorry, there's a question in the chat, which
yes.
would be good,
Yes.
which is if you could clarify how this chi on H acts.
Yes, I apologize for that. I was going too fast. Yes, this term here, what it does is that it restricts. It takes the part of your function that lives in the spectral subspace associated to this interval of energy. So if you look at the spectrum, let's suppose this is the spectrum of our operator, you will look at some energy interval. Let's suppose this is I, and what chi I is as this is a smooth characteristic function of this interval. And then what you do is that you take this function of the operator. You can do that using spectral theory. And what it does is really to select the part of your function that is associated to those energies that live in the interval. So that means that you're letting your function evolve in time, but only for that part of the function that in a way is associated to these energies, not the whole spectrum. And it is important also that we're looking at an interval. So in general, we look at intervals, or we want to say something about an interval, not about just one energy. This is not enough. For our purposes, we usually want to have an energy interval or the whole spectrum. Now, the consequences of this localization definition is that on one hand, well, the electrons do not propagate. That means that these functions that are the evolution of our initial state, they remain bounded, as I mentioned before, and the operator exhibits pure point spectrum. So that means that there are eigenvalues, and the eigenvalues have exponentially decaying eigenfunctions. And usually, I mean, this is for historical reasons, we call this Anderson localization, but what Anderson actually observed was what we call now dynamical localization. So just to make things simple, I'm just going to talk about localization from now on. And by localization, I do mean this dynamical approach, which is taking the unitary group, the exponential to minus IT, the operator, and looking at the devolution in T. Okay, so we have these two aspects then, dynamicals, how the wave propagates in time, and how the spectrum behaves, how the spectrum of the operator behaves. Now, another manifestation of disorder is what we call the Lipschitz states. So this is when we study the anti-graded density of states. So how do we study what is the anti-graded density of states? Is when you take your operator and you restrict it to a box. Usually, most of the methods that we use in the theory, we actually take the thermodynamic limit. So we restrict our operator to some finite volume, usually a box. Then we look at the discrete spectrum, we look at the eigenvalues, and then we take the limit when the box goes to infinity. Now, one can also count the eigenvalues. So for example, we restrict our operator to a box, and we can count how many eigenvalues we have below a certain threshold. So again, let's suppose this is our spectrum. When we restrict our operator to a finite volume, we will get some discrete spectrum. These are eigenvalues, and they depend on the configuration of the potential, so they're random. And one might be interested in computing how many eigenvalues do we have below a certain energy E. Well, this is what we call the eigenvalue counting function. If we normalize it, we will get a measure, and we take the limit when the volume goes to infinity, and this has a limit. If the operator is well behaved, like in our case, there is a limit, and this limit is called the anti-graded density of states. Now, we're interested, well, first in the existence of this object, of this function, and then how does this function behave? Because this is very useful for the purposes of localization. So here you see a plot. This is what would happen in dimension 2. The behavior of the anti-graded density of states when there is no disorder, when we either have minus Laplacian plus some periodic potential or just minus Laplacian, the behavior is like this. It's e to the power d over 2. In this case, dimension 2, just a straight line. But what happens when we add a random potential? This function changes drastically because the function decays exponentially. And exponentially, and we retrieve the behavior of the Laplacian in the exponent here. So this is another manifestation of disorder. And sorry. So first, one has to prove, of course, that this exists, and this is one uses some ergodic theorem to see. You can see this as an average of random variables in a certain sense. So ergodic theorem says that this exists in the limit, and now the asymptotics near the infimum of the spectrum. This is what we call Lipschitz states. This exponential behavior is what is called Lipschitz states, and this is a consequence of a large deviation principle that is acting on the background. So when one is computing counting the eigenvalues, what happens is that if our operator, so the Laplacian, suppose this starts at 0, our potential will have its average somewhere above zero. And therefore, to reach these values that are very low energies, we need to be looking at the infimum of the potential. The infimum of the potential, because the average of the potential is above zero. If we're looking at zero, the infimum of the potential, these are rare events. So this is why to reach the bottom of the spectrum, we need to be in a rare event, which has exponentially small size. And that's why we eventually get this exponential decay of the function. Now, this is important because we can also, well, first, it appears whenever we have disorder, usually, and it can also be used as an ingredient to prove localization with methods that I'm not going to discuss at the moment because they're very cumbersome, but one of the ingredients is this behavior. Okay, so there are things that are interesting for us, and let me just clear my annotations. So now what happens, we have this operator, and we know that in some parts of the spectrum, we have this dynamical localization. Now, what happens in the rest of the spectrum? We expect there is delocalization in some cases. So the opposite behavior. The functions, these functions that evolve on time, do not stay bounded for all time, but they propagate in space. That would be delocalization. Now, what do we know is that in dimension 1, we have that one can prove actually that there is localization everywhere in the spectrum. In dimension 2, people expect that this also holds, that there is localization in the whole spectrum, but we can only prove it at the moment for band edges or when the disorder is very strong. And there is a conjecture that in dimension 3, there is a transition. So in some parts of the spectrum, we have localized states, and in other parts of the spectrum, we have, usually in the bulk of the spectrum, we should have extended states. And we also have a transition between pure point and absolutely continuous spectrum. Now, this might remind you of what happens for random walks, this transition depending on the dimension. So the Laplacian is the generator of a simple random walk, in this case, the positive Laplacian. We know that in the limit, we have the Brownian motion, and there is this behavior of being recurrent and transient that looks a bit like these localized states, delocalized states, because in the localized states, they remain, if they started at one point, they remain at that point, I mean, nearby. And if they're delocalized, that means that they escape, they go away. And for the random walk, simple random walk, we have this transition that in dimension 1 and 2, the walk is recurrent, and dimension 3 and above is transient. And this is actually related to this transition for the random operator. Now, what happens when we introduce long jumps? And here I want to start telling you about some recent results that are inspired on what happens when we allow for long jumps in the random walk. So if we allow for long jumps, so now our particle can move not just to nearest neighbors, but everywhere on the line or on set D. And the probability transition, well, they all have to add up to 1, but here just to say that they will decay, let's take a probability transition that will decay as the difference between the points to some power b plus alpha. This will decay in a polynomial way. Now, if this alpha in the exponent is between 0 and 2, we know that this random walk will have a limit object that is the alpha stable Levy process that is a Levy process but allows for jumps. And the generator of that is the fractional Laplacian. So it's a minus Laplacian, so we have something positive, to the power alpha over 2, where alpha is this exponent here in the probability transition of the jumps. And there is a transition also depending on the dimension for these random walks. In dimension 1, there is a transition depending on the alpha exponent. So for alpha between 0 and 1, the walk is transient. for alpha between 1 and 2 is recurrent. So here it looks like a simple random walk. And for dimensions 2 and above, it's transient for every exponent. So it's really pushing, the fact that we have long jumps is really pushing for this rate, for this diffusion, for escape. And here are some reference people that have studied this transition. And now we would like to see, well, is this transition that we see here, depending on the dimension, can we see this on the random operator that we obtain by taking the fractional Laplacian and perturbing it by a random potential? And well, first, when we talk about the fractional Laplacian, so we want to perturb this by random potential. So what is the fractional Laplacian first? We can see this as a, well, as an integral operator. People have studied this a lot in the continuous setting as an integral operator, and it has many definitions. In the discrete setting, we think of it as a discrete integral form, and people have studied this in one dimension. They have studied how the kernel decays, which is exactly how it decays in the continuous setting. Diffusion, its relation to Levy processes, and more recently, in 2009, Paget and collaborators, they studied the fractional Anderson model. So they perturbed this fractional Laplacian by a random potential, and they studied the localization properties with numerics. So they did numerical analysis on this. And they showed that for alpha between 0 and 2, this exponent here, this model exhibits less localization than the standard Anderson model, that it would be with alpha equal to 2. Now, this is intuitive. I mean, it makes sense that this fractional Laplacian, since it's not local, is pushing for diffusion, while the potential is trying to localize. And one sees also, when we talk about Anderson model, we also see this as like a balance or a struggle. And we try to ask, well, which one will dominate? Is it the Laplacian that tries to diffuse, to propagate, or is it the random potential that will do? The fact that within the fractional Anderson model, there is less localization means that this is the effect of the fractional Laplacian there. And we wanted to see with Martin Gerber, my collaborator, if one could see this in, if one could have analytical results on this. So we set fractional Anderson model, and here we modulate the randomness by this parameter lambda. So let's assume, for simplicity, that this b omega is takes values between 0 and 1, so a random landscape or random variables on each side of the lattice as a height something between 0 and 1. And then this lambda allows us to move to increase the strength of the random potential or decrease it. Well, first, the kernel, this is no surprise, the kernel decays as in the continuous setting. So now we have something, so you see here this, this is like the decay of the probability transition. We have again a polynomial decay between points to some power b plus alpha, where alpha is this exponent in the Laplacian, fractional Laplacian. And what can we say is that for strong disorder, we can obtain that the spectrum is pure point and the associated eigenfunctions are not exponentially decaying, are at least polynomially decaying. Now we expect that actually they're not exponentially decaying, but so far we haven't been able to prove this. And what we obtained for the Lifshitz test that I had shown you before is that we are able to show Lifshitz tails, but now, of course, the exponent of this Laplacian appears in the exponent of the Lifshitz tails. Now, this all tells us that the Anderson model is a long-range random operator, and well, there are some results in the continuous setting. This is the first result in the discrete setting. There are some other results looking at the fractional Anderson model, but only from the point of view of Lifshitz tails, because Lifshitz tails, it's approachable via probabilistic tools. Because it's a mesh, one can look at it as a measure, and look at the Laplace transform, use Feynman-Katz formulas, use the properties of Levy processes, of alpha stable Levy processes, and obtain a lot of information on this function. And this is what Okura and Petrushka Pauva and Caleta did more recently, also for Anderson potentials. But in the discrete setting, these proofs don't work. There's things behave, they're not as regular. So one needs different tools to show this. And I think I'm gonna stop here because I think I'm already, already in my 25 minutes.
Yeah, you have maybe 2-3 minutes if you want, but otherwise we
okay.
can.
I have one more slide that I wanted to show you. Maybe. Okay, I'm not going to show you this slide. This was just to show you that localization for long-range models have been studied a lot, but this decay is very weak, the decay that we have from the random walk with long jumps. And this is not covered by any of the existing results. So this, at the moment, this stays, and the transition stays a conjecture. We don't know this. But actually, I wanted to take 2 minutes to show you another model very quickly where random operators also appear. And this is in connection with linearly reinforced random walks. Recently, there was this connection discovered by Sabot and Therese that they connect a linear edge-reinforced random walk with some hyperbolic sigma model that has been studied in the literature. Okay, that's not, I don't want to tell you about this, but in the mix and measure of these reinforced random walks, there is an operator, there is a random operator that appears naturally. And this random operator, people have conjectured, Sabot and Zheng have conjectured that the recurrence and transience of the edge reinforced random walk or the vertex reinforced jump process that is associated to the behavior of recurrence and transience is related to the localization and delocalization of this operator at the bottom of its spectrum. Now, this is, I would say, the closest thing that we are at, that there is in the literature to make a true connection between random walks, the behavior of transience and recurrence in random walks, and what happens on the localization, delocalization behavior of the operator. So this is very exciting. Now, it is very hard. We are at the moment working on this with Margarita Disertori and Xiaolin Zheng, trying to see if we can study this random operator that appears in this mixing measure and to see if this can tell something about, if we can relate it to the recurrence and transience of the random walk. But turns out, I mean, no surprise, this operator is quite complicated. So we're trying to see if the methods that exist in the literature can be applied to know something about their localization properties, the antigradient density of states. And we already see some surprises, like we can show localization in one dimension, but we're not in a Lifshitz states regime. So with this, I would like to finish and thank you for your attention.
Let's thank Constanza for the talk. Okay, so we have time for some questions from the audience. Are there any? So the methods you use don't really depend much. So maybe I missed something of what you said, but I mean in the case of the Laplacian, which comes from simple symmetric random walk, well, that one is fixed. But if you had a slightly different Laplacian, say, like if it comes from another random walk which is not the nearest neighbor, but still not long jumps, I guess everything still goes through, or you're using some special structure of these operators.
Actually,
this is a really long question.
What?
No, sorry. Go ahead. Since in the other case you didn't quite say what the jumps were, or.
So in the, because we either consider the Laplacian with nearest neighbor jumps, or the case of the fractional Laplacian with long jumps.
Okay, but
where the
so
long jumps decay polynomial.
Maybe to ask my question in a different direction, and this is just out of maybe ignorance. So if you take, is there an exact random walk model which corresponds to the fractional Laplacian? Is there a precise jump distribution for those, or it's more like it's a class of models which belong to that?
I would say it's a class of models that have this this probability transition. Sorry.
Oh, okay, right. So
it's this probability transition. This with alpha between 0 and 2. There is a restriction there.
Sure. Yes.
Because
okay.
this is I mean, if you take alpha bigger than that, then you're taking powers of the Laplacian.
Yeah.
For example, when we study the fractional Laplacian, we see it as a function of the Laplacian. We actually do a lot of spectral theory on it, seeing it as a function of the Laplacian, as Alessandra mentioned earlier, the B Laplacian with power 2. And you have all these problems with the restrictions to finite volumes. This is actually, there are also many problems with the restrictions to finite volumes with the fractional Laplacian. If you see it as taking a square root of the Laplacian or taking a fractional power of the Laplacian. There are also, and this is a big difference between the continuous setting and the discrete setting that we have, because in the continuous setting, people work with a certain type of boundary conditions, and in the discrete setting, we actually have to we can use some analytical results from having Dirichlet, Neumann boundary conditions at the same time, and to have some relation between them. But it's actually very tricky. That I would say that's the hardest part to deal with the boundary conditions, because for everything that we do, we first look at restrictions, and then we take the limit when the volume goes up to infinity. But to get the limiting objects, then so you see, localization game is about. It's not just enough that the limit exists. It's really that you have to look how it behaves in the whole space.
Right.
Yeah.
Thanks. Any other questions? Okay, then otherwise let's thank Constanza again for the very nice talk.
Thank you.
And